Now let's work on this problem of calculation of total fluid pressure and force on a submerged plate. As we discussed at the conclusion of the last lecture, the really important key uh, property that we'll use about fluid pressure is this fact that the pressure exerted by water at a point, which is say d meters below the depth of water, is the same in all directions, and that's really useful. So before we start the problem of fluid force on this entire plate, let's first uh, calculate the pressure exerted by water at a particular point, which is d meters below the surface, this scenario right here. So to do this, we will return again to our simplified model of a horizontally situated plate, which is say 1 meter on a side. It looks pretty small, but there it is, 1 meter by 1 meter, and the column of water sitting above this thing. Right, and again, let's suppose this thing is d meters deep, and we want to calculate the fluid pressure right here on the plate. Well, to calculate the pressure, we first need the force. The force is equal to the mass times acceleration due to gravity. The mass, in turn, is given by the volume of the column of water above it times the density. So we multiply that times gravity. Volume times density is force, and for that we get what? Well, the volume of water is the volume of this column, which is d meters deep times 1 meter on a side, and density of water is 1,000 kilograms per cubic meter, and acceleration due to gravity will just, well, it's 9.8 meters per second squared, but we'll just call that g. And so what do we get here? For this force, we get 1,000 dg. Now, to calculate the pressure at this point, of course, we take the force and divide it by the area. But the area of this plate is just 1 meter squared, so we just get 1,000 dg divided by 1 meter squared, or 1,000 dg. Sorry, let me write my answer down here. 1,000 dg newtons per meter squared, or again 1,000 dg pascals. If you're working with some other fluid besides water, then the number that'll change here will be the density. In general, density is often denoted with the Greek letter rho, so you might often find this pressure written rho d g units or pascals. So that's the pressure at a point which is d meters below the surface, rho dg. So now let's return to this problem, the problem of calculating the total fluid force on this entire plate. We know the pressure now at any depth d. If we pick a little point, the pressure at depth d is rho dg. And of course, we want to calculate the total force on the entire plate, which is determined by the contribution of pressures at all of the different points on the plate. Of course, infinitely many of them. Now, the problem, as mentioned before, is that the pressure applied to a point up here on the plate will be drastically less than the pressure applied to a point down here at a greater depth. So that's the subtlety that we need to address. To do so, we can make an approximation. And we'll make an approximation by calculating first the force exerted on a thin horizontal strip out of this plate. Let's assume that this strip is at a depth of x meters below the surface. Now, you might argue that the pressure exerted on this plate vertically will change as well as you go through the depth of the strip. But if the depth of the strip is small enough, say delta x meters, then the force, or the pressure, will differ only by a small amount as you move from the top to the bottom of this very thin strip. And so you can find a good approximation of the total force applied to this strip. And of course, the other fact we're using is that the force will not change as you move horizontally across the strip. So what's the total force applied to this strip? Well, this can be calculated by finding the pressure located across the strip times the area of the strip. So we know the pressure that was obtained over here. So this is rho d g. We can even include units in here to make sure that conceptually we're doing the right thing. The pressure is in units of pascals per, I'm sorry, that's incorrect. The pressure is in units of newtons per meter squared, and that's pascals. And the area is in units of meters squared, of course, and so with a little bit of dimensional analysis, you see that the meters squared cancel out and you are left with newtons for total force applied to the plate, as you would expect. So what do we get in this case? Well, the pressure is rho dg, and the area is, well, what do we have? I didn't give you the length, I'm sorry. Let's assume that the width of the total plate is, say, L meters. So we have L meters times delta x for the height. The depth of the plate is given as x in this particular scenario. So we have rho times x times g times L delta x. And whoops, our units, of course, here would be newtons. That's the total force applied to this particular horizontal thin strip. Now, to obtain the force that the entire plate experiences, of course, you're going to have to do this not only for this thin strip, but the thin strip that lies directly below that, and then the thin strip that lies directly below that, and so on and so forth. Of course, then to gain an approximation for the total force, you can subdivide your plate into n such horizontal strips and find points, or depths, I should say, x1 through xn, and repeat this calculation for every such horizontal strip located at depth x1, x2, x3, and so on and so forth. Then to find the total force, you need to add up all of these contributions. You do so by forming the following sum, as I goes from 1 to n of pressure times the depth, this will be the depth that changes, times acceleration due to gravity, times the length of the plate, times the constant width of each one of those strips. And of course, that is only an approximation. As we do with all of these processes involving integration, we move from an approximation to a precise value for the force by taking the limit of this expression as n approaches infinity. And this expression, limit of this sum, should be recognized as a limit of a Riemann sum. It is precisely an integral rho x g L delta x upon the limit as n approaches infinity is transformed into the infinitesimal dx. The limits of integration, well, will be where x begins and where x ends. In our scenario above, it looks like the plate was situated so that its top was coincided with the surface of the water, so it began at depth 0 and it moves downward to the total depth of the plate, which I did not give you in this problem, so let me just write depth, total depth for the upper limit of integration. So there we go. Of course, in the calculation of this integral, you should recognize that a lot of this stuff is just constants, the rho, acceleration due to gravity, and the length. And so all of those constants in this particular case can be moved out to the front of the integral, rho g L, and then you're just integrating x dx. So as far as calculation goes, it's a relatively simple integral to calculate. Now we'll do another example in just a minute where the plate which is submerged won't be a rectangular plate. And that was the story that we had a minute ago. We had a rectangular plate. But more generally, surfaces vertical surfaces which are submerged may not be in the shape of a plate. For example, we talked about a hydroelectric dam whose shape was not a rectangular plate but a trapezoid. Or your plate might be some hatch underwater which is in the shape of a circle. So these different geometric problems will require some further and more careful analysis. In particular, this length of the strip that we saw right here won't be a constant as you descend through the depth of the surface, or the surface, right? And so you won't be able to pull that outside of the integral. Rather, this length will be some function of x, which will change as you move down the surface. So in the next video, we're going to do an example of a surface of non-constant width and see how we can set this up to calculate the total force exerted by the fluid on the plate.